We'll see how to do that in Python. So for instance, you may get the data in terms of days, but you can convert it into weekly data. You can get it in terms of minutes. You can convert it to hourly data and so on. It's all that is possible. Sometimes and then you can also, there are cases where you need very small intervals, like when you are measuring heartbeats in medicine. The heartbeat is essentially a time series. Measured over time. So in those cases, the time intervals are usually really small, maybe less than a minute in some cases. Just could be a second, every second. So these are some of examples you can encounter where you may find time series useful. In the financial world, they study stocks using time series. In the energy, you can consider electricity consumption for a household or for a whole region. In meteorology, you can study temperature over time. That would be a time series. So there are many other time series, like the audio signals are usually just time series. Those can also be studied. In fact, there are some that have been studied and used to classify different genres of music and so on. That may not have been done for the local. That may be an opportunity for the local environment, because I think that has not been done locally. The local songs and so on, they may be a good thing if they can be studied. And time series techniques can be used to study that along with machine learning and be able to classify our cultural songs. Though we will not look at that today. So this is an example of a time series. It shows the daily power consumption of a region in Morocco. So this is publicly available data. I will share the source of this in the slides. Something went wrong with my slides and I had to fix them. So I didn't finish the references section. I will do that after the talk. And when the slides are shared, you will be able to get the source of this data. These are some of the use cases for time series. So maybe you can go back a bit. You can observe some of the changes that happen as you go along time. So this is the things we'll be trying to look at. You can see there's some from the early parts of the year, there's some trend going up. Then towards the end of the year, the power consumption seems to go down. And those are the things we'll be trying to observe when you plot a time series. Even before doing an analysis, it can give you a rough idea of what is going on. So there seems to be a lot of, in this particular region, there seems to be a lot of power consumption somewhere in the middle of the year. That might be explained maybe by temperature and so on. We will see that other variables may be able to explain the different variations. I think we have mentioned these use cases already, but these are some of them, and there are some benefits to them. If you are in business, they can minimize your stocks, your inventory. You can manage your inventory better. And if you know exactly what you need, you can improve your negotiations with the supplier. And if you know also the demand for your products, you can tailor your campaigns better. So there are three main components that we will consider for time series. The first component which you may not see directly by just looking at the time series is a trend, or you may not be able to see how it moves properly. We'll be able to extract a trend. This is the long-term movement in the data, so you can helps you tell whether it's increasing or decreasing over time, and it can increase and decrease within that period. It doesn't have to be unidirectional. Then there's a seasonality, which is made up of changes that happen over specific periods. So they can occur monthly, they can occur weekly, and we will see some of that as well in the demonstration. Then there's a random aspect of the time series. This is the unpredictable variations which cannot be explained by the trend or the seasonality. And when you add all this up, you get the time series. There are situations where these can it's multiplicative. So then instead of adding these up, they are multiplied. But we shall not consider the multiplicative option. But these are the important things. The trend will tell you the movement. Seasonality will give you the cycles, how it changes over time. And then the randomness is the unpredictable part or the noise, what you can't account for. So another important property we look for is stationarity in time series. And this means that we want a time series whose statistical properties do not change rapidly over time. They remain relatively constant across time. This may not always be the case, and you may have to transform your time series before you can do the analysis. And one of the ways for doing that is differencing the series. I don't know whether I should do some illustration of differencing. Let me see if this will work. So differencing works like this. If you have a time series, so suppose let's take numbers that are easy to work with. So this is not realistic, but these are numbers that are easy to work with. So the differencing basically means you get the difference, say, between the first and the second. So 2 minus, this is not a good one because they will all be the same values, but that's what differencing will do. So now your new time series becomes this one. So you will lose some values, but now the new time series, which gives the differences between the values, will be able, will smooth out the properties and make probably give a series a constant mean and variance throughout. And when that happens, now it's easier to apply some of the methods that we want to apply. In some cases, you may need to do some transformations using the logarithm to stabilize the variance and so on. But we'll just focus on differencing. We will not do any log transformations. So the basic idea is stationarity is good for the models. And so it means when you transform the data, then you can apply the model. But since the transformed data is not what you want to predict, you'd have to reconstruct the data again after prediction, because the predictions will be on the transformed data. Okay. So let's move on. So that's just the core concept. Now, the one other organization can give you a lot of information. This one we already seen earlier. It's a time series for power consumption of a region in Morocco. So I will move on to the next part of visualization. Now, this one is simulated data for cells. And the other thing you can do is highlight some important events. For instance, if they are special to other people. This one we have seen. So the next thing is you can compare 2 or more time series. So initially we had shown this power consumption for this blue colored line curve. It's the one that was the power consumption we had seen. But now we're able to compare it with 2 other regions in Morocco. So you can see there are 2 time series. This blue and orange seem to vary in the same way. So the power consumption pattern seems to be the same in these 2 zones. But the green one seems to have a fairly different consumption pattern. You can see where the others are going up, it goes all the way down. And it's, for the most part, it seems to have this green region seems to have more, seems to have lower power consumption, with a few exceptions, just somewhere midway. It has a spike. It doesn't outdo the time zone, the zone 1, but it's able to outdo zone 2 in this period. But in almost all other places, it's below the other zones. So so you can aggregate over larger time periods. Like we can pick all the different days of the week and get the mean consumption for the different days. And you can see we have Friday all the way up to, this is not ordered properly, but we'll order it in there. So different days have different consumption patterns. So Sunday seems to have low consumption for these two zones, but this third zone seems to have higher consumption on Sunday and lower consumption on the other days. So these are some of the patterns you can extract from the time series. If you are in business, you can look for days where the demand is low. That can determine the stocking that you do, the staffing, and so on. You can make yourself more efficient, so you don't overstock or you don't overstaff on days when there is low demand. For this, it is power. So this can help the people generating the power to schedule their generation better. So you can also extract the components that we mentioned earlier, the trend, the seasonal component, as well as the noise or the residual component. So this shows the trend. For this, the original one is up here. Then you can see the trend. For the first part of it, it seems to be going up. The middle part, it's relatively stable, and then it goes down again towards the end of the year, the consumption. So this gives you the trend. The seasonal one seems to have cyclic patterns. You can see there's some repeating ones. You tell cycles. Right? Now this is measured daily. So there could be cycles of 7 days. That is about a week. So you have weekly cycles. Then at the bottom is the noise, and this is a random aspect which you cannot account. So it's possible to, within a few lines of code, to split the time series into these components. So the other thing you can do is autocorrelation. Autocorrelation simply shifts the time series and does a correlation with itself, but shifted by a number of lags. So this autocorrelation helps you to determine the appropriate model to use. If you had more time or a more detailed presentation, we would go into the details of how this can help you determine the appropriate model to use. But some of the things you can pick up from this are the seasons. I think in the code we shall see an example where we can pick up the season. This first one does not show the seasons, and also can tell you that, for instance, this first one is the autocorrelation, and since it is not dying out quickly, it means you cannot use the moving average model for this. This second one is a partial autocorrelation, which measures is a little different from the autocorrelation, but this one now tells you, you see, it dies off just at the second lag, and that gives you the order of the model. In this case, we shall talk about it later, but it tells you should be considering an autoregressive model for this series. So the other thing that can help you see trend are the moving averages. So if you have some very spiky or noisy data, sometimes you may not be able to see the trend clearly. Moving averages will help you see that. So it just picks 3 sequence. So that's this one helps you to smooth. I hope you can hear me.
Yes, hello? We can hear you.
Okay. So this helps you to see the trend. Here we just did a 3-month moving average. You can do a longer moving average to really smooth it out and see the trend better. So the 2 main models we will consider are the moving average models. Again, I won't go into the details of this because we shall run this in the code. So the moving average is a model which simply uses the error from the current and the previous observations to predict the future, and the autoregressive model uses the previous values of a time series to predict the future values. So moving average, then you can have combined models where both aspects are taken into account. So these two work very well when the data is stationary. In other words, the statistical properties do not vary as you move along time. This would, if you had a longer talk, then we'd go into the details of this. So if the data is not stationary, sometimes you have to do some differencing, and then you use the ARIMA model. Now, the ARIMA model does not handle seasonality very well. So if you have some seasonality, we can apply the SARIMA model. All this is done by the software, so you don't need to worry about that so much for now. There are some parameters that you have to put in, but also the software has a way of computing those parameters automatically and trying to find the best by itself. We'll get to that as we do the demonstration. So SARIMA takes care of the seasonal variations. If there's seasonality in your data, then SARIMA will be able to do a better job of prediction than just pure ARIMA. Once you run models, you can do some predictions. If you're happy with the model, we've done some prediction. If you look at the orange, this is part of the time series. Then we've cut off a piece of the existing time series. So if you look at the orange is the observed time series, the actual values for the time series. And then the green ones are the green line here shows the predicted values. So the predicted values here will be able to assist you tell. If for instance, you are at this point, you'll be able to predict what happens in the future. So the green one is a prediction. It pretends we didn't know what the actual values are and then predicts. Now we can compare those and do some analysis to see whether a prediction is use the mean squared error and so on. But there are ways of checking that. There are also some other diagrams for diagnostics, diagnostic plots that you can put. So for the previous cases we have looked at, we have not considered external variables other than the variable being measured across time. But it's possible to have models that can account for more of the variation using different variables. So for instance, if you are predicting sales, you can add market spend as a covariate, and hopefully that can improve the time series. That doesn't always happen, but in a few cases it will help do that. So there are models that handle these extra variables, and they're called the exogenous variables. So ARIMAX is the one that may not take care of the seasonality, and SARIMAX takes care of seasonality, but also they handle the covariates as exogenous variables. So these covariates can also be used as features in machine learning models. We shall not be looking at the machine learning models today, but they can also be used to study time series. So these are the examples of machine just listed here, but we shall not be looking at this today. These are things that one can look at later and do some further research. So the other thing you can do is compare two different time series. So you could do two things. One, you could compare the raw time series, and this simply checks the core movement of the raw time series. But this may not be reliable because it can be affected by trends and non-stationarity. So you may get a spurious correlation of some sort, which is not correct. It is not quite true. What's more reliable is to get the correlation of returns. The returns are the differences, the change, the percentage changes as you move across from one point to another in time. The percentage changes are what we call the returns. So the correlation of the returns is more reliable. And if you want to compare two time series, that is a better metric to use than to just get the correlation of the raw time series. So this tells you whether the two time series change in the same direction or not. I think it also shows you the volatility. How do they vary? How do the changes vary as you move along? So these are examples of percentage change. So you can see there are some days when there are sharp changes in consumption, especially in the first two graphs. There are some days which have really sharp changes in power consumption. This last one doesn't have very sharp changes until towards the end of the year. Towards the end of the year, there are some days when there are very sharp changes between days, and so on. So this is what we call the percentage change. Now you can get the correlation between one zone and the other using these values, and we shall see that in the demonstration. When working with machine learning techniques, you may need sometimes to get more features, and some of the features you can get are the moving averages, or what we call the rolling statistics. They can be moving averages, standard deviations. They help to smooth and highlight the trends. We saw an example of that, but that same moving average can be used as a feature to improve a model or as an exogenous variable. We saw earlier we can extract month and day, quarter. We saw weekly data that was able to tell us how the consumption of power across the days of the week. And these can also be used as features in models. There are other techniques to study time series, like the Fourier transform, which can identify dominant cycles, which can help you reconstruct the series using those dominant cycles, or even make predictions now using the dominant cycles. Then the same things we saw earlier, the trend, seasonal, and residual components can also act as features. And we've seen, we already mentioned that the features are supposed to improve your model. And it takes a lot of experimentation. As you work with your time series, you keep trying some features. There are models that can tell you which features are more important than others. You can drop some and keep the others and keep working on the series until you get a good model. Again, we shall not be covering the machine learning methods for handling time series. So these are it's just information. So make the predictions or the model are listed here. The smaller the value, the better. The smaller the value of the metric, the better. That is true also for these AIC and BIC. We pick models that have the smallest values. So if you are running several models, the ones with the smallest values would be the best models. You can also do cross-validation if you are doing machine learning. Now, if you're doing cross-validation for time series, you have to remember that you cannot train on future values and predict on previous values. So the splitting into the testing and validations and training sets is a bit different, and one has to be careful when doing that. Though we shall not cover cross-validation today. So I think we mentioned this already about the correlations between two time series. We've also now correlation in finance is quite useful. I think they use it to measure risk. And so on. So a good thing is to, when you are trying to evaluate your model, is to check it against multiple metrics. And anytime you get new data, you update the model for better predictions. So it's also good to ensure that data is up to date and correct, consistent, accurate, and so on. Regularly retrain the models as new information and new variables are obtained. And then you align it with your different campaign schedules and promotional strategies. It can help communicate across departments and so on. These are just the business side of the. After you're done with the analysis, now you can use this. Now you can automate the process also. Usually, if you consider platforms, it can be on a dashboard so that someone can just look at it from a dashboard and see how sales, the trends are for sales and marketing spend and so on. So we are about to go to the live demo. I don't know if there are any questions before we go to the live demo. I will add more the references. Like I said, I had to fix the presentation. The last minute, something went wrong, and I did not add the references on time. So I will add the references before we share the slides. So there are many other things you can do with time series. This presentation is by no means exhaustive. There's it's simply not possible to cover everything in 1 hour, but I hope it gives a hint of what you can do with time series, and then we will see more as we go to the demonstration. Are there any burning questions now, or should we just go to the coding?
Dr. Katende?
Okay, so yes.
Yeah, there's a question in the chat asking from Rennie, maybe highlight more on correlation of time series. How can one manage on data stationarity?
Okay, there's no one size fits all answer to that question. I think you'll have to treat different situations differently. So what we'll do, maybe during the coding, you will see a few of that being handled. Part of it is the differencing that we mentioned earlier. Differencing helps to stabilize the mean. Sometimes you may have to do the differencing more than once, but then you'll observe at then there are tests. They are the test and check whether your data is stationary. I think there's augmented Dickey-Fuller test or something like that. The ADF test that can help you. Given that the target audience was supposed to be the general audience, I did not go into the technical details so that we don't lose anyone. But if there's interest, we can organize for something more technical and answer some of the deeper questions. So I'd like to go to the code. We'll start with this data on power consumption. So we shall need a few packages from Python. Like I said, this will make more sense. It would be easier to follow if you already know Python. If you don't know Python, I think you can focus on the output. We'll try to explain the output, and hopefully that will make sense. So we usually need some packages to do the analysis. So we shall import those. And the data is in Google Drive. We'll import the data. Still waiting for the connection to Google, the runtime. Behave. So now we are connected to the runtime. I think it should load the data. So the data is now loaded. I will also share this data. Once we get all the emails for the attendees, I think we shall share the slides and, along with the data and this script as well. So once you load the data, the first thing is to just look at the variables, inspect them. So this is the data. It has all these consumption. It is measured every 10 minutes. Power consumption, temperature, humidity, wind speed, general diffuse flows. I think this may be something about the pollution. Then what is of interest to us mostly is the power consumption. We have power consumption for zone 1, zone 2, and zone 3. So there are 3 zones whose power consumption was measured, and it's stored in this file. But then we have other variables that we may wish to use to explain the variability in the consumption. So these are what we can use as the features, or if you're working with the ARIMAX or SARIMAX, you can use this as your exogenous variables. But most of the time, we shall just use the values in the time series itself for our presentation. So you can inspect the data also and see, in this case, there's no missing data, there's no missing data at all. Again, that is something that you need to consider when working with time series. We will not cover it today. So then you can go into visualization of a time series. Let me make this figure size a little smaller. It's too bulky. So we view the power consumption in zone 1 and along with the temperature. So what we compare along over time. So remember, this one is measured every 10 minutes. And that may not be a good measure for our case. We'll see that it looks a bit too noisy when the time interval is too small. Then we can fix that after. Takes a bit of time to do that, so should be done shortly. It is not in a hurry. So here it is. So you can see if the time intervals are too small, the data is too noisy, you can't see any useful patterns in it. The same happens with the temperature. The time interval is too small, 10 minutes, and you can't see any useful patterns easily. So what we do is we you can, there's a function for sampling it to daily, so it averages over a day and gives you the mean consumption for that day. So that's what happens in the next block. And then if you do that and then you plot, this time you have plotted more variables. You can see now the patterns are clearer, but now this is on a daily basis. So the data has been aggregated to a daily interval. You get the mean consumption per day, but we actually, this is the total. We have used sum instead of mean. So this gives us a total consumption. So this is what we have. So this gives you the power consumption for the three zones. These first two seem to have similar patterns, and the last zone seems to have its own very different pattern. So the first zone goes as high as 38,000 and maybe a little lower than 28,000. The second zone can go as low as 16,000 in consumption and about as high as 28,000. And then the third one can go as high as 30,000, can also go as low as 10,000. So you can see the ranges within which the power consumption is for those three zones. You can compute the descriptive statistics just to get the means, the quartiles, the minimum value, standard deviation, and the maximum. So this is done for each numerical variable. We'll not look at that for now. This is the daily consumption for zone 1. We had already seen this. So we can plot all the consumption for all the three zones in the daily consumption for all the three zones in one graph. And this is what you get now. At this point, you can make some remarks and you're able to compare the different patterns in the three zones just visually. At this point, you're not doing predictions yet. So at the next point here, which labels the day of the week. It also labels month for date and also the quarter. So if you check now, we have added 3 more variables. It's day of the week, there is month, and the quarter. So the Python is able to pick the date and extract these items. It can tell you the day of the week, can tell you the month, and it can tell you which quarter of the year you're in. So each value is labeled appropriately. So we need to order the weekdays so that when you plot them, the order is correct from Monday to Sunday. You can order them the way you want. If you want to start from Sunday and as a first day, or in any manner you wish. So once we order the week, we can now get the average consumption on a given day of the week. And that's what we do here. So for zone 1, we can see how it works. The consumption, the labels are down here. They're using the same labels. So Monday is the first day, Tuesday, Wednesday, Thursday, all the way up to Sunday. So how it works, you can make this smaller. So how it works is you can now see the pattern. For this zone 3, it's fairly stable all the way up to Thursday, goes really low on Friday, spikes on Saturday, and a little lower on Sunday. For the other zone 2, we have all these changes, keeps going up, and then goes down again all the way. It's quite low on Sunday. For these 2 zones, they seem to have the same patterns of consumption. So this puts all of them on the same scale, and you can see that one zone consumes a lot more than the others. This one also consumes a little, somewhere in the middle. And the last one is a zone that consumes very little. But the patterns in these first two zones look the same. This third one looks very different from the other two. So instead of doing it by week, we can do it by month. And this is what we get. So you can also see the patterns across the months. So that's what it looks like from January all the way to November. The data was collected over 1 year. And now we have aggregated it over months, so we can see how it moves across the months. If you are looking at sales data, then you can align your strategies to what you see. There are months where you may need to do more, months where you may need to do less. So you can also compare using box plots for the different days. This is for zone 1. So for zone 1, again, you can see the consumption was low on Sunday. There's some variation, no outliers so far, because if you have outliers, you would see values beyond these bars. For this, doesn't seem to have unusually high or unusually low values. That's for zone 1. We could try this for one other zone and see if it gives us. I can change this to zone 3. Because zone 3 seems to have a totally different outlook. So zone 3 seems to be, there are some days with unusually high values. These are the outliers. Then they don't have, and they don't have really small outliers. So that can help you analyze the time. You can also use these density plots. Again, this one is for zone 1. Yes.
Dr. Katende?
Hello?
Steve Wasila was asking if we can use IQR in the chat box. Yes.
Okay, let me see if there's more context to the question. He was asking if
you can use IQR.
So the interquartile range is, you can see it from the, what do you call it? This box plots. So the interquartile range shows you the variation. So this is a first quartile. This is a median. So 50% of the consumption is above this point and 50% is below. So this is a middle 50% of the data. Then the interquartile range would be the difference between the first quartile and the third quartile. So this already shows you the interquartile range between these two. Then this, you extend these whiskers. This, you add 1.5 times the interquartile range to the peak of these whiskers. So if there are any points beyond that, they are So this gives you some density plots. I will skip this. Now this gives you box plots, but by quarters. So before we were studying this by days of the week, how the consumption is for different days of the week. So this one shows you the consumption along different quarters of the year. So the first quarter, I think this is for zone 2. For zone 2, the first quarter seems to be fairly low consumption, has some low values. These are outliers that are caught outside. The second quarter has slightly higher values than the first quarter. The third quarter of the year goes higher and then low again in the fourth quarter. So the next part extracts the components of a time series, the seasonal, the random component, and the trend. So that's the trend. It appears. These are the seasonal variations. Later on, we shall see the length of each seasonal variation using some autocorrelation plots. So this shows all the different plots in one graph, but you can plot them separately. You can extract them and plot separately, which is what is done here. I'd already run them earlier. So you can, this one shows you the trend separately, how it varies across the year. And this is a residual. So this residual can also be used to pull out outliers. We will not do that in this because we don't have enough time, but you can see these, some of these points which are very long peaks, they shoot out. These could be points that are outliers and they can affect your model. So it may be good to kick them out. You can use these residuals to find them and kick them out or replace them with the mean or some other statistic that makes your analysis much better. So the next thing we look at is the percent change, which we had talked about in the presentation. We do that for each zone. We do the percentage and add a new variable to show the percent change for each zone. And I think after that, we plot the percent change. So this shows how power changes from day to day across the year. So you can see how it will vary. Maybe from one day it drops quickly. If it was demand, for instance, this one on this particular date, it drops from here to fairly low to and shoots up all the way, then goes down again. But this shows you the daily variations in power consumption. Basically, how the percentage of change from one day to the next. So there are days when you can have as much in zone 1, you can have as much as 15% drop or rise within one day. Between 2 days, rather. You can also have, in this zone 2, I think this is slightly more than 20, maybe about 25. You can have as high as 25% jump between in consumption between days, 2 days. Zone 3 doesn't seem to have a lot of jumps for the first part of the year, but towards the end, there are some days where there's a lot of fluctuation in terms of change in demand between days. So you can also compare two time series. We can do, this is a scatter plot of the zone 1 time series and the zone 2 time series. And you can see on average, they seem to increase together. When one is up, the other one is up. When the other one is low, the other one is also low. So they seem to be correlated. The consumption in zone 1 and zone 2 seem to be positively correlated. You can actually compute that, and we use a heat map to visualize this. And you can see zone 1 and 2 have a 0.6 correlation. Zone 3 is weakly correlated to either of the two. So zone 3 has its own different pattern from zone 1. So this is the correlation between the percent change, not the raw data. The correlation here is between the percent change. The correlation between the raw data can also be computed, but sometimes it is not reliable. It may work in some situations. So you can have a situation where the two series are correlated highly. So we can do
I believe Dr. Katende has dropped out. Let's give him a few minutes to rejoin. Thank you. As Dr. Katende rejoins, I think we can have a brief chat. So how is everybody finding the series? Is it okay? Yeah, please share your views and your opinions. Thank you, Steve. Anyone else? And also, what other topics would you like us to cover?
Hello, you can hear me?
Yeah. Yes, we can hear you, Dr. Katende. Welcome back.
Yes, my internet is really misbehaving.
Oh, okay.
So let me share the screen again. So I think we are at around this point. So the other thing you can look at is autocorrelation. They are not random correlation. So there's something you will notice here. Pattern in this autocorrelation. So this 7, so that means there's a weekly seasonality. There's a weekly seasonality in your data, and that can be useful when working on the model. So at the next point, we do the forecasting. We use the automated forecasting that is done by R. So there's will fit the model automatically for you. It will run through all possible cases and try to find the best. And even after it finds what it calls the best, that is just a starting point for you from that point and add for your data, but it saves you time. Of course, there are some parameters you can
Dr. Katenda? Bota.